Hi, my name is Alexey Artyomov. In this video, we present Deep Estimators of Features, DEF, or DEFs, a learning-based framework for predicting sharp geometric features in simple 3D shapes. This is a joint work with Albert Matveyev, Ruslan Rakhimov, Gleb Bobrovskih, Vagiy Yegiazaryan, Emil Bogomolov, and Evgeny Burnaev from Skoltech, and Daniele Panozzo and Denis Zorin from New York University. For human-made 3D shapes, such as this CAD model, we seek to deliver an accurate reconstruction of geometry and topology for both straight and curved feature lines, displayed in yellow. To this end, we leverage large collections of annotated geometric data and learn highly efficient patch-based deep convolutional models of distance-to-feature fields for range scan data, or depth images. To combine the inference of local distance-to-feature predictions into a complete estimate for a full 3D shape, we deliver a view synthesis-based approach and reconstruct coherent, high-quality distance fields for the entire shape. We build on top of that and demonstrate the usage of our distance field in a downstream application, where we extract explicit representations of parametric feature curves from raw range scan data. Estimation of sharp features has been studied extensively in literature. In our work, we compare to 4 state-of-the-art methods belonging to different groups: normal estimation-based Voronoi covariance measure, or VCM, and data-driven ECNet, PyNet, and sharpness fields, or SHF. Most methods that we analyzed demonstrate various drawbacks. Some require per-model tuning of parameters for feature detection. Others are prone to noise. Others tend to miss features in undersampled regions or spuriously produce false detections. This motivated our search for a more comprehensive learning-based solution. We start by generating synthetic training data using the ABC dataset. Our data generation pipeline accepts as input a set of meshes and their associated feature annotations, basically edges marked as sharp. We extract local triangulated patches and associated interior sharp feature curves. We acquire ray-casted depth images and sampled point clouds. We then compute local distance-to-feature annotations. Each patch comes with a small and fixed number of samples. We use 4,096 samples per patch. Ultimately, we produce a set of sampled local patches with distance-to-feature labels in each point as output. In this way, we obtain synthetic collections ranging from 16,000 to 256,000 training instances. We focus on sharp feature detection, which means that large values of the distance-to-feature function have little impact on feature localization. We define a truncated distance-to-feature field dP in each location P. We find for P its closest neighbor Q located at one of the sharp feature curve segments gamma, and compute distance as a Euclidean distance between P and Q. We truncate the distance by selecting an appropriate truncation radius. To compute this quantity in practice, we start with paying attention to a local patch of a 3D CAD model and ignoring the rest of the model. Extracting this patch produces a mesh fragment consisting of 7 surface regions, S1 through S7, along with 6 associated feature curves, gamma 1 through gamma 6. To identify features that should be included in the distance computation over a particular surface region, we construct a surface region and feature curve adjacency graph, where each surface region and feature curve sharing mesh vertices are basically connected by an edge. For samples living on S7, in this case, naive computation of distances would find closest points on gamma 5, which is rather counterintuitive. In contrast to compute more natural distances, we exclude non-contour curves for each surface region by constructing a pruned surface/curve adjacency graph. In this way, for S7, all but gamma 6 features get excluded. Overall, the same depth data may be annotated differently, depending on which adjacent feature curves are included when computing distances. We distinguish between interior, contour, and proximal exterior curves. Features appearing as a contour of a sampled region are captured by an insufficient spatial context for inferring these from point samples. Exterior features pass within distance truncation radius epsilon but still outside the visible patch. Regressing these from the local patch context would be impossible due to the absence of samples covering them. In contrast, we generate the per patch annotations locally in each patch using only feature curves passing through the patch interior. In this way, both adjacent surface patches are sampled. But how densely should we sample a shape? Well, sufficiently densely for the presence of feature curves to be inferred from the positions of samples. This leads us to have a generally adaptive number of point samples per object. This is a common practice in high-quality 3D data acquisition, adapting the number of points per object and sensor placement to the geometric complexity and size of the object. Here's one way to reason about sufficient sampling. We start with a parametric CAD model consisting of surfaces and curves. We then analyze each curve individually and compute its linear extent, or maximal linear dimension. Ordering the curves by this quantity, we can relate a sampling radius R to features of characteristic spatial size, sampling these with at least n points. Our characteristic spatial size L is a linear measure set to the 25 lower quantile of the distribution of sharp feature curve extents, and we sample such curves with 8 to 50 samples depending on the data variety we use. To support generalization to real-world scanning data, we also constructed a dataset of 84 real objects and semi-automatically annotated them. We opted for fabricating the models with known geometry using 3D printing and produced shapes directly from CAD models. We then used a commercial structured light 3D scanner to acquire the geometry of fabricated objects in the form of depth images. We semi-automatically registered all scans to their respective CAD models using an initial alignment from the scanner, followed by optimizing it in MeshLab for tighter fits. The result is the first real-world dataset with exact, sharp geometric feature annotations. We train our deep models by solving the standard learning task. Given a set of n-training instances, minimize the loss. We have considered multiple options for elements in this setup to identify an optimal learning configuration. We compare various losses. We assess gains from additional inputs by concatenating prior sharpness estimates, ground truth normals, as well as both of these values to the point coordinates. We also train networks with richer supervision from additional network heads, regressing either normalized directions, or both, and we evaluate a number of image-based and point-based neural architectures. The best performing choice of architecture turned out to be a CNN UNet with ResNet 152 backbone trained using the histogram loss using the supervision from ground truth distances only. But what if the models see sparser inputs than what they saw during training? So we have found that our trained networks are able to detect even significantly over or undersampled features, yielding either a proper distance field or a scale transformed proximity field whose isocontours still capture true features. The result demonstrates the generalization ability of our deep models that are able to robustly predict features in real scanned 3D shapes after fine-tuning it on a subset of the real-world dataset. We have compared our method versus competitors using clean and noisy image datasets. In terms of feature segmentation, most methods struggle to detect subtle features, produce substantial amounts of false positives, or inadequately process large density variations and noisy inputs. Our deep models are able to more accurately perform segmentation. Similar is valid for distance-to-feature regression, particularly on noisy inputs. Now, how do we actually predict a complete set of sharp features for a full input 3D object? First, we extract a collection of overlapping patches by scanning an input shape from multiple viewing directions. We then process each patch using a depth network to obtain patch-based predictions. These are sensitive to interior sharp feature lines only. You can see also that features on the contour of the shape are not detected. We leverage the multiple view stereopsis machinery to transfer distance-to-feature fields to adjacent views by reprojecting and linearly interpolating single-view predictions. The final estimate of our field on a complete 3D model is obtained by a robust statistical inference procedure. So, starting from a set of partial and inconsistent estimates, we reconstruct a distance-to-feature field defined globally on a complete 3D shape. For our experiments on reconstructing feature curves for the full 3D shapes, we use 128 views and perform view synthesis and orthographic projection. We extract minimum value for the final statistical estimate. Qualitatively, our method is able to more robustly regress features with smaller difference in normal orientations, undersampled features, or those with large density variations across the feature line, such as those in internal cavities of the shape. We then decided to evaluate the quality of distance-to-feature fields reconstructed using our method and designed an algorithm for extracting parametric feature curve networks employing the estimated fields. We start with a reconstructed distance-to-feature field with threshold distances to obtain a subset of samples that we use to estimate corner probabilities and construct curve instance segmentation. Here, on the right, the black clusters are corresponding to the detected corner areas. The detected corners and curves allow building and optimizing a curve graph that reflects the surface connectivity. We finally translate the curve graph into a set of accurate parametric curves that reflect feature geometry of the reference shape. Making a number of careful parameter choices, we are able to fit accurate feature curves networks. To assess the wireframe quality, we compare our pipeline to PyNet and the ground truth parametric curves. We use distance field estimates obtained using for the entire 3D shapes obtained on large-scale point clouds of up to 10 million points. Likewise, we compare versus point cloud to wireframe, which is a recent learning-based wireframe extraction approach. Note that this method outputs straight lines only. In this way, our method is more robust and flexible and is able to deliver more complete reconstructions. We also examine the noise sensitivity of our method by training DEF-CNNs on datasets with increasing noise levels and varying sampling. We can see that actually our method is quite robust with respect to density and noise variations. Crucially, for the completeness of the reconstruction, sufficient number of views must be provided to capture most features. We investigate how the performance depends on the number of available views and perform fusion using 2, 4, 8, 16, 32, 64, 128, and 256 views. Overall, we have presented a new learning-based pipeline for automatic sharp feature detection from sampled 3D data. If you're still interested in detail, please read our work and don't hesitate to reach out. Thank you for watching.